the structure in the vicinity of a water body, vehicle impact, braking, and temperature. So starting off with dead loads. Dead loads are basically the category of loads wherein the self-weight is to be multiplied and transferred to the substructure. So they are a permanent category of loads. Okay, they have to endure this for the entirety of their service life. The self-weight of the structure is usually calculated by the software which you are using. Okay, so if you want to be sure of your results, you can have also manual calculation done simultaneously. Okay, also there's one more thing that it is not always the case that you'll have equal spans on both sides. If you see the sketch, you have span 1 which is 20 meters and span 2 which is 30 meters. So obviously the loads, this is the top view. Let us assume that we've got 4 bearings. So if it is 100, so maybe this is 50 and this is 50 from right hand side. And when this is 50, then it will be 25 and 25. So depending upon the spans on either sides, right hand side and left hand side, you will have the dead load values changing every time. So it depends mainly upon the type, number and section geometry of the girders, span and length. As you said, type. So you can have a case wherein over here we've got I section girders and over here we've got box girders. So of course, even if you have got such an arrangement, maybe you've got 4 I section girders or 5 I section girders, and we've just got over here 1 single box girder. So maybe even if this being 20 meters, maybe this will have more load. Maybe this will have 500, or maybe this will only be 200. So this can be the case. So it is not only about the span, it is also about what is the type of girders, what is the number, and what is the section geometry. Superimposed dead loads. As I said, the DBR, the design basis, has to specify what is the superimposed dead load which is incident upon the span. So that includes long welded rail pads, fasteners, parapet wall, OHE masses, like in one of the models that you saw, which had street lights. Okay, solar panels, if we have a provision for solar panels, cable trays, plinth loading, and others. Okay, so this has to be specified by the DBR. This has to be specified by the DBR. So this is a typical picture of this is one of Dubai Metro. So these are the stations. So if you see on the track, it is not only a plain deck. So over here we have got rails, we have got plinths, we have got some utilities. Over here we have some railings. If at all we've got some street light over here, then it has to be represented as load. Then if you've got conduits like this running, you have to have all of them included in the SIDL load case. So this is the long welded rail. Long welded rail is basically the railway. So this is a case, like for example, if you have got a case wherein it is one of the tracks, like this is track 1. Okay, this is track 1 and track 2. But over here you've got a merging track. Okay, so the over here the plinth, the concrete plinth which is going, it has to merge into a second track. So how you will take the SIDL load case? This is a representation of that. Like for example, the red block indicates a curved track, and the gray block indicates a straight track. So when it is merging like this. So at one point, at the midpoint, you can say, it will almost be like one single plinth. Okay, so why I'm showing you this is because if you have to simulate exact conditions, you need to know, like for example, if one single block is weighing maybe 10 kilonewtons, it is just an example. So over here we've got only the dead loads, which is 10 plus 10. But at this juncture, we have only got 10. Okay, maybe it will have some extension, so maybe it will be 12, not 20. So this has to be represented. Why? We cannot risk having excess loads without any reason. So because we need to have it as a proper simulation, so this should be simulated. So over here, if you see there's one protruding element. Over here it is not. So maybe over here it is 10, but maybe it is only 7 over here. So it depends upon what is the level of detail you want in your model. Okay. All right, so live loads. Live loads are basically the bogie loads or the axle loads that must be specified by the DBR. So the design basis should also tell you what is the axle load, what is the loading that you have to be designing the structure for. So over here, this is a typical metro bogie that I've indicated over here. These are the axle loads. Okay, 16, it is ton, 16 ton per axle. Okay, so in the top view, one of the wheels is 8 tons, the other wheel is exerting a load of 8 tons. So all these details, all these tonnage values have to be specified by the DBR. Okay. Of course, in the software that you're modeling it, there are some predefined vehicles, but only if it is allowed in the DBR or if it is the client's requirement, you'll use those. Otherwise, you'll have to define a separate vehicle with these distances. Okay, and make them run on the model. They'll also specify the number of successive cars. Like, for example, over here, I've shown you 4 successive cars. They'll show you, okay, we are only planning on having 6 successive cars, one after the another. So based on that, you will have to define your bogie in the software. Okay. All right, yeah. So I'll show you a small animation of live loads. Okay, so this is okay, so this is a typical elevation for a pier and span arrangement, girder arrangement. So this is span 1, this is span 2, and we are assuming that we have got only 2 tracks. Okay, so when we have got only 2 tracks, what are the possible number of variations of live load that we should consider? Okay, so this is indicating that. Over here I've mentioned 8 tons, but this is only for one side. Okay, so it is actually 16 tons per axle. So this is the case wherein only single live load is moving over the span. Okay, this is a train which is moving on the left hand side track. So this is a case wherein a train is moving on this part of the span, only a single train. So now this is a case wherein 2 trains at the same time are running on the track, but now they have stopped on the left hand side span, or you can say the span 1. They have stopped on span 1. This is a case wherein 2 loads, two trains have consecutively passing, but they are on the same side of the spans. And now this is the final case wherein both the tracks and both the sides have been loaded. So these conditions have to be properly simulated. Okay. Moving on. You need to create possible combinations of live load. So for example, if you see this image, you will realize that there are only 2 tracks, this track 1 and the track 2, but there's also a merger of track. There's also merging track. So this gives rise to a number of variations that the span could possibly experience in its service life. So this was actually a span which I designed for North Mumbai Metro, and this was you can say the number of tracks that I experienced. So this is a trapezoidal span. Okay, and on the trapezoidal span we had 3 number of straight spans. Okay, so these are straight spans, track 1, 2, and 3. But we've also got mergers. This is track 4 and 5. So now you need to properly simulate and prepare as load cases all the different track conditions that could possibly be experienced by the span in its serviceable life. So having done that, these are the possible variations. So we'll assume, so all of these are live load cases. Okay, you have to create all these live load cases in the model. In my case, I did it on Vidaswell. So we are assuming that only a single train is going on the bridge span. So this is case number 1, T1. Single train is going on track 2. This is T2. And similarly, it is on track 3. It is going on track 3. It is on the T3, on track 4, and on track 5. So these are single train load cases. On double train load cases, we can say that okay, T1 and T2 at the same time, 2 trains are running on these tracks. Similarly, all these variations have to be taken in consideration. And the main cases, 3 trains are running at the same time. So tree 1, 2, and 3, all of them are occupied at the same time. So all these cases must be properly represented. So it makes up total to it gives us like 14 variations. So these are 14 variations which will possibly present us with the challenge of finding out what is the highest value of torsion, what is the shear, what is the reaction, the bending moment values for which we should design a different girder sections. Braking and traction role also. When a vehicle is stopping on the track, it will exert a longitudinal force, as well as when a vehicle is starting off from its rest position, it will also exert a certain load. So it is taken as 20% of the live load. Wind load, like you'll have to refer to the wind load Rose diagram of that area to get the exact value of the highest wind speed. And similarly, you'll have to put the load on your structure. Okay, this we had discussed. Okay, finally, we have got earthquake loads. As I told you that seismic arresters are a unique member which is placed upon pier. So basically what the seismic arresters do is that they bear the impact of the transverse loads. Okay, seismic arresters are responsible to bear the impact of transverse and longitudinal forces. So depending upon what direction of forces they are actually resisting, they are called as transverse seismic arresters or longitudinal seismic arresters. Many times you can also have a seismic arrestor which is resisting what do you say, earthquake loads in both the directions. It is doing a job of a longitudinal as well as a transverse seismic arrestor. So that would be called as a of course transverse and longitudinal seismic arrestor. So more on this. I believe you remember the model that we had spoken about that I showed you upon it. That was a seismic arrestor. I'll show you one animation wherein it will be clear as to why exactly we are considering seismic arrestors. Okay. This is a small animation for the different forces on a pier. Dead load. We have studied about this. Self weight coming from the top, the box girders, the pedestals, the pier cap, the pier, crash, and the foundation. This is the wind load diagram. Wind on the superstructure. It can be resolved into uniformly acting force. Okay, the geometry has to ensure that most of it is deflected. Wind is also impacting upon the bogie. Yes, this is the impact force. Why do we need crash barriers? This is why, because it is possible that a car might actually dash. So it is important to consider this load case. Live loads we have seen, seismic loads now. Okay, if you see the sections, longitudinal and the transverse section, in between we have got the seismic arrestor. So the girder is actually trying to hit the seismic arrestor. I've over-exaggerated the condition, but it would not be so high. It would be in some mm maybe, but I've exaggerated in order for you to better understand this. Okay, this was the longitudinal impact. So if we have a seismic arrestor which is taking the longitudinal impact, it will be called as a longitudinal arrestor. Similarly, for transverse, if it is taking a transverse impact, it will be called as a transverse arrestor. And if it is doing both, then it will be called as a transverse as well as a longitudinal arrestor. Water current loads also. Okay, so this is why we have seismic arrestors. So when we are actually designing a seismic arrestor, this is a case for an arrestor being a transverse as well as a longitudinal. So this is a longitudinal force which is acting on the section, the height of which is 1500, the length is 2000, and this width is 700. So when we are talking about longitudinal design, this section, this figure has to be taken into consideration. So over here, the beam, the member is 1500 meters long, but the point at which it is acting, it defines the shear span. So this is your shear span, and this is your depth. So in this case, when the force is acting over here, will resolve the structure from over this part. So in that case, we get 1500 as the length and 700 as the depth of the member. So naturally, it is supposed to be designed as a bending member or a corbel. Okay, if you see over here, we need to know what is the shear span to the depth ratio. If it is less than 6, then we'll design it as a corbel, and if it is not, then we'll design it as a bending member. Similarly, in the transverse direction, this is how the forces and the shear span will be taken. some additional forces, vehicle collision loads, launcher loads, water current loads, buoyancy, centrifugal